Welcome to this session on drilling optimization, well-designed process to execution. This is sub-module 3 of 4. In this module, we'll focus on torque and drag modeling, hydraulics, and mechanical earth models, looking at both design and execution phases. Let's begin with the objectives for this session. In this sub-module, our goal is to strengthen your understanding of the modeling tools used in both the design and execution phases of drilling operations. First, we will look at torque and drag modeling and understand how it applies to different drilling activities such as rotating, sliding, and tripping operations. Next, we will apply this modeling in both design and execution to assess limitations and monitor performance. We will then shift to hydraulics modeling, exploring how fluid flow through the drill string and annulus can be predicted and optimized for better drilling efficiency and equipment reliability. From there, we will examine how real-time measurements enhance the robustness of these models and help predict failures before they occur. Finally, we will introduce the role of mechanical earth models in design, stability management, and real-time monitoring. Torque and drag modeling is one of the core tools we use to anticipate how the drill string will behave under different operations. Essentially, it allows us to calculate the forces acting on the string so we can plan for equipment limitations and ensure safe, efficient drilling. We begin with rotating off bottom, where the drill string is turned without weight on the bit. This highlights the baseline torque from friction. Then, during rotary drilling, torque increases as weight is applied, cutting formation and creating cuttings transport challenges. In slide drilling, where we use a bent motor assembly, the drag profile changes because only axial force is applied without continuous rotation. When sliding in or tripping in, drag becomes a key factor as the string is moved into the wellbore without drilling. The opposite, tripping out, introduces overpull and potential sticking risks. Finally, during reaming and back reaming, the torque and drag responses highlight wellbore condition, rugosity, and cuttings beds. Together, these scenarios demonstrate how torque and drag modeling provides the framework to predict where problems may arise and to design strategies that mitigate risks. Next, we'll see how this modeling supports design decisions. In the design phase, torque and drag modeling is essential for planning both the drill string and bottom hole assembly. By simulating forces along the planned trajectory, we can test whether the proposed BHA configuration will deliver the required weight transfer and bit control without exceeding mechanical limits. Trajectory design is another critical aspect. By modeling drag and torque across various inclination and azimuth builds, we can identify sections that might cause excessive side forces or high friction factors. This allows adjustments to the well path before execution, reducing the risk of stuck pipe or premature tool failure. Rig equipment selection is often the limiting factor. For example, if the torque requirements in the plan exceed the rig's top drive or drawworks capacity, we need to either change the well design or bring in different equipment. Modeling highlights these mismatches early. Finally, torque and drag analysis identifies operational limitations, such as maximum depth before buckling or excessive drag during tripping. These insights ensure that the design is realistic, executable, and within safety margins. With design covered, let's now move into how torque and drag is applied during execution. Once operations begin, torque and drag modeling moves from prediction to monitoring. The key focus is wellbore condition. For example, hole cleaning can be evaluated by comparing actual drag data against modeled values. Higher drag may indicate cuttings accumulation. Similarly, torque deviations can suggest instability or poor hole cleaning efficiency. Wellbore stability issues such as tight spots, rugosity, or spiraling often appear as unexpected increases in drag while tripping or while reaming. Tortuosity, the degree to which the actual well path deviates from plan, can also be detected when measured torque and drag differ from the model. Buckling of the drill string is another condition we monitor closely, as it can increase drag dramatically and lead to stuck pipe if not managed. Each of these indicators allows us to assess real-time wellbore health. By comparing measured data to modeled predictions, we can quickly identify deviations, diagnose potential problems, and adapt the drilling program. In short, execution phase torque and drag modeling is a continuous feedback loop. Measure, compare, and respond. From here, we'll transition to another critical modeling domain, hydraulics. Hydraulics modeling is the study of how drilling fluid behaves as it moves through the drill string and annulus. The objective is to predict flow conditions and pressures under different operational scenarios so we can optimize hole cleaning, bit performance, and downhole tool functionality. At its simplest, hydraulic models account for drilling with constant circulation, but more advanced software can simulate a wide range of conditions. For example, off-bottom circulation shows baseline flow behavior when the bit isn't cutting. Rotating versus non-rotating modes account for annular velocity changes when the string is in motion compared to static conditions. Variable flow rates and varying depths also influence pressure drop, annular velocity, and cuttings transport. By modeling these conditions, we can predict how equivalent circulating density, or ECD, will evolve, and we can anticipate challenges such as pressure surges, losses, or inefficient hole cleaning. Next, we'll examine hydraulics in the design phase. In the design phase, hydraulics modeling is all about planning and optimizing how the drilling fluid system will perform. First, it is used to support BHA and drill string design. By modeling fluid flow, we can ensure that cuttings are transported efficiently and that the BHA receives sufficient cooling and cleaning. Bit nozzle selection is another key application. Nozzle sizes directly control jet velocity at the bit, which impacts rate of penetration and cuttings removal efficiency. A hydraulics model allows us to balance pressure drop across the bit with annular cleaning requirements. Trajectory design is also informed by hydraulics. Different well inclinations and depths change annular velocity and equivalent circulating density, so simulations can identify high-risk sections where pressure or hole cleaning may be problematic. Rig equipment selection comes into play when we compare modelled requirements with the rig's pump capacity and standpipe pressure limits. Often this becomes the practical constraint. Finally, hydraulics modeling predicts expected tool performance, particularly for mud motors or other hydraulically powered equipment. This ensures that tools are operated within their designed pressure and flow rate ranges. Now that we've covered design, let's look at execution phase hydraulics. In the execution phase, hydraulics modeling shifts from prediction to active monitoring. A primary focus is wellbore condition monitoring. Here we track annular pressure and equivalent circulating density. If the measured ECD exceeds the fracture gradient, we risk losses. If it drops below pore pressure, influxes become possible. By comparing measurements with modelled expectations, we can keep the operation within the safe window. Monitoring equipment performance is another vital use. For example, pressure drops across the bit or the motor can be compared to predictions. If the motor shows a larger than expected pressure drop, it may indicate wear or plugging. Likewise, if bit pressure drop deviates, it could mean nozzle erosion or blockage. Hydraulics modelling also helps us understand the effects of operational changes. Adjustments in flow rate, pump strokes, or fluid properties can all alter downhole pressures. By recalculating in real time, we can anticipate how these changes impact performance and avoid unplanned events. Hydraulics is a balancing act between surface equipment, downhole tools, and wellbore conditions. Next, we'll consider how measurements improve our models and help predict failures.
My name is Yasid Arevalo. I am the Drilling Optimization Product Champion for Schlumberger, and I'm going to talk to you about our high-performance drilling motors. Have a rotor stator feed that goes through a 3D profile along these contact lines, and that's what makes the seal for us to produce the power. This is a very complex phenomenon, so we have modeled all of that. The contact between the rotor and the stator also is quite complex. You see the deformation of the rover. You will experience variable friction factors as these happen. The deformation of the rover also leads you to these hysteresis cycles, and basically this creates temperature cycles that produce fatigue in the elastomer. So by modeling all of this accurately, we're able to predict how long is the life of that elastomer in any operating condition under any operating parameters. So we know if the elastomer is going to last enough to cover the whole run or the whole job, and we can also find what the best power section is for that application. The other very important factor here is the fluid behavior within the rotor stator cavities. So that plays a very huge role in this, and it is something that is also very complex. And if you add things like the bending of the motor as you operate it, all of this is incorporated into the model. And what we have seen is that we can very accurately predict, for example, the time it takes under a certain environment, meaning temperature, mod type, etc., and operating conditions, when will the elastomer start to fail and start to chunk. And we have seen maybe within 5% in terms of hours. Within a few hours, we can know that point. So that allows us to be very aggressive on the drilling parameters, and also to select the best configuration. So the other thing that we're looking to the future is how can we actually use that in real time. And as you run your operating parameters, you know how aggressive and how much gas you have left on your motor, basically. So how much further you can drill and push that motor to get the maximum performance safely and reliably. This is an example of that in action, basically. And we picked this example because this is a very mature field where we have many wells drilled by motors, and so we have a very well-established baseline. And in this case, we picked the candidate power sections, and these power sections that come up as best are not always, or I would say most of the time, not intuitive, not what you would pick from the paper power curves. Because that's the other thing you model. You model the actual downhole power of the motor. That doesn't have anything to do with what you see on a paper specification of the motor. So by knowing the true power, so you compare things like maximum stall pressure, the fatigue life, the RPM on bottom with your actual operating parameters. So once you compare all of these for your motor, you can choose the best one using this modeling, and then you can run it in whole. And the results here were the first run with this power section was the top 5 within the top 5 runs of probably 100 wells that were drilled in this field. And then the second run was the best ROP in the field. And that's what we want to achieve. That's what we want to do. We want to model what the best power section is for your application, and then pick that and get this top 5 or top ROP every time. Thank you very much.
A mechanical earth model, or MEM, is a comprehensive representation of the subsurface mechanical properties at the planned well location. It combines geological, petrophysical, and geomechanical data to give us a structured view of the forces acting in and around the wellbore. Key components include pore pressure, which determines the fluid pressure within formations, fracture gradient, which defines the pressure required to initiate fractures, and in situ stresses, both vertical and horizontal, which influence how the formation responds to drilling. The model also incorporates wellbore stability parameters such as rock strength and elastic properties. Together, these factors define the safe operating window for mud weight and guide decision-making on trajectory and casing design. Without a reliable MEM, we risk instability, losses, or even catastrophic well control incidents. This high-level overview sets the stage for how MEMs are applied. Next, we'll discuss their role in the design phase. During the design phase, the mechanical earth model is central to planning a safe and efficient well. One of the first applications is defining the mud weight window. By mapping pore pressure against fracture gradient, We can identify the safe pressure range that prevents both influx and losses. Trajectory design also benefits from MEM input. High stress formations may require adjusting inclination or azimuth to avoid unstable zones. Likewise, knowledge of stress orientation helps us choose well paths that minimize breakout or collapse risk. Risk analysis is another major use. By simulating possible wellbore instability scenarios, we can identify hazards before execution. This leads directly to procedure definition, where mitigation measures are built into the drilling program, for example, contingency mud weights, casing depths, or non-productive time reduction strategies. So in design, MEMs act as the blueprint for stability and safety. Next, we'll see how MEMs are applied during execution. Once drilling begins, the mechanical earth model becomes a live reference tool. It allows us to monitor wellbore conditions and update our understanding as new data comes in. For example, measured pressures, caliper logs, and drilling parameters can be compared against model predictions to confirm or adjust stability margins. Event analysis is another critical application. When issues arise, such as unexpected losses, tight hole, or stuck pipe, the MEM provides a framework to diagnose the cause. Was it related to pore pressure variation, stress orientation, or an underbalanced mud column? By tying events back to the model, we learn and refine future decisions. Management of change is the third key area. Conditions often deviate from plan, and the MEM helps justify operational changes. For instance, if pore pressure turns out higher than predicted, the model supports raising mud weight or adjusting casing depth with a clear geomechanical rationale. With torque and drag, hydraulics, and MEMs covered, we can now review the module objectives. Let's take a moment to review the objectives we set out at the beginning of this submodule and reflect on how we've addressed them. First, we aim to understand torque and drag modelling across drilling operations. We looked at scenarios such as rotating, sliding, tripping, and reaming, and discussed how torque and drag help us anticipate mechanical limits and wellbore conditions. Next, we focused on applying torque and drag modelling in the design and execution phases. We saw how modelling supports drill string design, trajectory planning, and rig equipment selection during planning, and how in execution it provides real-time indicators of hole cleaning, stability, and buckling. We then evaluated hydraulics modelling, covering how it guides nozzle selection, tool performance, and rig limitations during design, and how it monitors ECD, pressure drops, and tool health during execution. Another objective was to see how measurements strengthen models. We demonstrated how real-time data aligns or diverges from predictions and how this feedback improves reliability and failure prediction. Finally, we applied mechanical earth models to design, stability management, and monitoring, showing their role in safe mud weight windows, risk analysis, and change management. This concludes submodule 3 of 4 on drilling optimization, design and execution. Please take a moment to proceed to the quiz, which will help reinforce the key concepts we've covered. Thank you for your time and attention, and I look forward to continuing with you in the next module.